properties of wave. So first, general wave properties. So you know, wave is something like this, move up and down. So that's the wave. So example is sunlight, for example, visible light. Visible light is this kind of wave. We call it transverse wave, which is here. Okay, so you see the first point. Wave transfer energy without transferring matter. Without transferring matter. So example, sunlight. They transfer heat. Okay, they transfer thermal energy, which is heat. They never transfer any matter. The sun never send any metal, never send hydrogen, helium to us, you know, although it is the burning of the hydrogens to get the heat, but it never send the hydrogen or the helium to us. So the hydrogen, helium remain at the sun, never transfer matter, just transfer the energy, the heat. Okay, second point, frequency. The number of wave passing any point per second measured in hertz. Okay, so to understand frequency, I give one example. So let's say you have 20 hertz. 20 hertz, that means 20 wave passing a point in 1 second. 20 wave. What do you mean by 20 wave? So you see here to here is count as one wave. So one wave, two wave, and so on. 20 wave passing through a point in 1 second. That is 20 hertz. So that's how we understand frequency. And formula of frequency is frequency equal to 1 over period. And we have to know that period is the time span for one wave. One wave. So one wave is sometimes known as one complete oscillation. So the time span from here to here is the period. So when we talk about period, right, so you have to be careful of the graph. You know, sometimes they put graph as displacement versus distance. And I put a graph like this. Sometimes they put displacement versus time. And they put the graph like this. Okay. So we have to know that if they give distance as the x-axis, then what we get from one wave is the wavelength. The wavelength, lambda is the symbol for wavelength. If they use time as the x-axis, then what we get is period. The period is capital T. And you put the period, the time span to make one wave, you put into the formula, you do 1 over period, and you get the frequency. So that's the thing. Two type of graph. Be aware of the horizontal axis. Okay, now the third point, period. Time taken for one oscillation in seconds. Time taken, okay, for one oscillation. So this is one oscillation. How much time is spent? That is period. Wavefront, the peak of a transverse wave. So this is the peak. The peak is also known as the crest. The crest, the peak of the transverse wave forms the wavefront. Wavefront looks like this. That looks like line, you know. Okay, like this also. These are the wavefront. This is the wavefront. Okay, so wavefront is actually something like this. Let's say this is your wave. Okay, this is your wave. So whenever we see the peak, we draw a vertical line to represent the wavefront. So this is another wavefront. So here is another peak. So this is wavefront again. So wavefront are these vertical lines. Okay, all these straight lines are wavefront. Okay, so that's why they say wavefront is the peak of a transverse wave or compressions of a longitudinal wave. A longitudinal wave, I give one example. Longitudinal wave is like this one. Okay. Longitudinal wave, you can see certain part is separated further apart. Certain part is very close. So this part is called compression region. And this part is called the rarefactions, compression, rarefaction, compressions. So that is longitudinal wave. And the wavefront is in the middle of the compression. You draw one line to represent the wavefront. So this is wavefront. This is also wavefront. So wavefronts are like that. And wavefront is between one wavefront to another wavefront, so you can get the wavelength. So you see, you can get wavelength in this way from the starting point to the end of the, the wave. Or you can also get it from two maximum or two crests or two peaks. In between two peaks or two crests, that is wavelength. So it's written here. So it's between crest and crest, wavelength. Now we see speed. How fast the wave travels measured in meter per second. So how fast the speed travel, how fast the wave travel. So for example, one of the famous example is how fast light travel. Light travel at the speed of 3.0 times 10 to the power of 8 meter per second. So this is how fast the light travels. Light is a wave, just for your information. So it travels at this speed, 3 times 10 to the power 8, very, very fast. Cannot imagine. Okay, so that is the speed. And of course, to find the speed, there is a formula. The formula is, okay, I temporarily point it down here. The formula is given here. To find the speeds of the wave, we take the frequency, multiply with the wavelength. Frequency times wavelength equal to the speeds of the wave. So frequency, you can get it from here. Or you can get from this graph, you get the period, then you do frequency equal to 1 over period. So you get the frequency, you get the wavelength, multiply them, and then you get the speed. So that is the formula to find the speed. V equal to F lambda. So we have two formula already. Frequency equal to 1 over period, V equal to F lambda. Okay, now next one, wavelength. Distance between a point on one wave to the equivalent point on the next wave in meters. Equivalent point. For example, crest to crest. If you don't want crest to crest, you can take throw to throw. Throw to throw means minimum to minimum. If you don't want minimum to minimum, then you just take origins to the next origin. Okay, so this one may be just afraid you misunderstand, or can I take here to here? No? Here to here cannot. Here to here is not wavelength. Because wavelength, after one wavelength, you must see the same thing repeat. You must see the wave come up and down and up again. So must have the same pattern that repeats after the wavelength. So that's the wavelength. Amplitude is here to here. So that is the amplitude. It's the maximum displacement, or they use maximum distance is fine. Maximum distance a wave move from its rest position. Rest position is the x-axis itself when a wave passes. So the amplitude is here. Or you can take here also as the amplitude. Now, in this graph, you can see amplitude and wavelength. Crest, throw. Okay. Now let's see the two different types of wave. We have transverse wave, which is of this shape, moving up and down. Longitudinal wave, they use a slinky coil and you shake it left and right, then it forms something like the longitudinal wave, where the coil is compressed in this region, is stretched at this region, compress, stretch, compress, and stretch, which alternates. Okay, so that's longitudinal wave. Longitudinal wave, remember example, sound. Sound wave include ultrasound. Ultrasound. Sound, ultrasound, longitudinal wave. Transverse wave, what example? Just remember, any kind of wave other than sound wave and ultrasound that we heard so far will be the transverse wave. What kind of wave we heard? Like the previous chapter, we discussed about the electromagnetic wave, radio wave, microwave, infrared, visible light, ultraviolet, X-ray, gamma ray. So those are all transverse wave. More common one, water wave. Okay, so the vibrating string from the guitar or violin. So they are all transverse wave. A lot of examples for transverse wave, but longitudinal wave, just sound wave or ultrasound. Ultrasound is just sound also, So kind of easy to remember longitudinal wave, and other than sound wave and ultrasound, the rest will be transverse wave. Transverse wave, you have to move your hand up and down to form the model of transverse wave. Moving up and down means that the particles is also moving up and down. So imagine you have a particle here. So what happens to this particle is they are moving down, then up again. So it's just moving up and down. The particles at this region will move up and down. Okay. What go forward is the energy. Energy is going forward, but the particle is moving up and down. So let's see how they put in words. Traveling wave in which oscillation is perpendicular to direction of travel. So remember the term used. What move up and down is oscillation. Oscillation is up and down. It's vertical. Direction of travel is go forward. Go to the right for our case. So for example, water wave. Water wave from the seaside. The water go in front. The water wave go in front. That is the direction of travel. And the oscillation is up and down. Up and down. So how to imagine the thing is up and down? So you just put a float or maybe a boat at the water wave, then you can see the float or the boat moving up and down. So it shows the oscillations of the water wave. Okay, so what move in front is the water and the energy. Okay, so now has crest and throws. Crest maximum, throw is minimum. Okay, and for example, light, not just light, all the electromagnetic wave, water wave, vibrating string. Okay, now let's compare. You see the keyword is perpendicular. Now this one is parallel. Parallel. Okay, so let's see. The traveling wave in which oscillation is parallel to direction of travel. So the oscillation is left and right. Left and right, which is horizontal. The direction of travel is to the right. So which is also horizontal. So that's why we say they are parallel, because left and right and going to the right are just two parallel lines. So they are parallel. This one perpendicular, this one parallel. And you must remember clearly what parallel with what. Oscillation parallel with direction of travel. Must remember clearly. Don't just say parallel. You can't get the marks. As compressions, so here, here, and here. And rarefactions. Rarefaction is the part which is stretch. For example, sound wave. Okay. Now, formula, speed equal to frequency times wavelength. So, okay. Let's move on. Okay. Before we look at the phenomena of wave, so let's go through some questions first. Okay. So I will find out some suitable question for practice. Yeah.
Okay, sir.
Okay, let me check through first to find out which question is suitable for us to try at this moment. Okay, let's look at B. Part B only. So part B. A device at the bottom of the sea emits a sound wave of frequency 200 Hertz. So this is frequency. The speeds of sound in seawater is 1,500 meter per second. So this is V. Okay, so calculate the wavelength of the sound in seawater. Wavelength. So are you able to think of what formula to use to count the wavelength? Wavelength is lambda. So you see F, V, and lambda. So you have to think of formula V equal to F lambda. Then you substitute. The V is 1,500. The F is 200. The lambda is unknown. And then we have to calculate this out. So we take 1,500 divided by 200. So we get 7.5. 7.5 is meter. So 7.5 meter is the wavelength. Okay, so we can only do B part 1 as warming up question. The rest we haven't learned yet. Okay, now let's see whether we can do any other more question or not. Okay, so We look at multiple choice. Okay, so the question that we can do, for example, we can do questions 21 on the left. 21. Which row shows the nature of light wave?
No, which page is it?
This is on page 14. Page 14.
Okay.
So which row shows the natures of light wave, sound wave, and X-ray? So as you can see, longitudinal and transverse. Okay, correct, and correct. Yes, C is correct. So only sound wave and ultrasound is under longitudinal wave. So no problem with this. Okay, now let's continue. Let's find other question, which is okay. Now let's see this question. This is question on page 15. The frequency of a wave is double. Become 2f. The speed of the wave does not change. The v is the same. What happens to the wavelength of the wave? So wavelength. So we think of v equal to f lambda. The speed does not change, remain as v. Okay. Let's say this one I set up to unknown. Initially it is f1, then after that it double and become f2, where f2 equal to 2f1. This one same only, v. After that still v.
Is the answer D, sir?
Half. Correct. Okay, so I just put in the calculation to let you see only. So f1 lambda. So when the frequency is double, become 2f1 lambda. Okay, then you can see your lambda is v over 2f1. This one is v over f1. So you can see this one have divided by 2 already. So meaning that it half. So divide by 2 means it's half. Okay, so D is correct. Then you can see the same question, and let's just move on to see what else we can practice. Okay, no more already. So we can't practice anything. So we just continue. Okay, let's continue with the notes. Okay, now we have refractions. Refractions is the bending of the wave. Okay, so let's see more details here. First point, speed and wavelength is reduced. During reflection, the speed decrease, the wavelength decrease. Okay, so V equal to F lambda is our formula. So based on the first point, they say the V decrease, the wavelength decrease. But frequency stay the same. This one, same. Same. I use S to represent same. And the wave changes direction. So directions change. For example, you can see this one straight, now bend down a little bit. So the direction change in refractions. So in what situations reflection happens? Of course, we need to know one by one. In water, how to make reflection happen. In maybe in, let's say in light, how to make refraction happen, so we need to know one by one. Okay, so we see the information first before we discuss on that. Waves slow down when they pass from a less to a more dense material and vice versa. Okay, so example, light. Reflection happens when the light travels from air to into a piece of glass, for example, from air into glass. So air is obviously less dense because this is air. Glass is obviously denser because this is solid. So this is denser. Okay. So that is one way to make refraction happens. And the second way to make refraction happens, which is on water. So to make refraction happens on water. So example, from deep region into shallow region. So deep region is taken as the denser one. Okay, let's say I follow the trend here because less dense to dense, right? Okay, I follow the trend. Okay, so to follow the trend, let me see first. From A into glass, slow down. From deep to shallow. Oh, okay. From deep to shallow, it slow down also. From deep to shallow. Yeah.
So isn't it deep is like nearer to the normal, and then when it goes to shallow area, it becomes away from the normal?
When it go to shallow, as you can see here, it is towards the normal. Towards the normal. You can see it from here. We will discuss this in details. Okay. So from deep into shallow. Okay. So that is where the water is refracted. Okay. Now, does it slow down or not? So you can take it in this way. You imagine at the seaside, right? So the water from a deep region to the shallow regions around the beach. So the water slows down and it stops somewhere at the beach. Okay, so that is how we seal it. It slow down. So it slowed down. Okay, so from here to here, it slowed down. Slow down. From air to glass, it slowed down also. So of course, the point here they say from less dense to more dense. So this is counted as less dense than less dense. This is denser. Denser. So of course we can take less dense and denser in this way. So when the region is deep, right, the H2O are separated further apart, less dense. When it's shallow, then the H2O are closer together, that is denser. Okay, so the region is smaller, right? They are closer together. So we can see it in that way. And now let's see the next point. When water is slowed down, it is reflected towards normal. So from air to glass, it is reflected towards normal. So I draw a pictures to let you see. Okay, let's say this is the air and the glass. The normal must draw perpendicular to the boundary. So the light move to this point, then they are closer to the normal, towards the normal. So how we see towards the normal? You can see the angle. So this angle is known as I. This angle is known as R. It's always come from the normal. So you can see the I is greater, but the R is smaller. Okay, I and R. Okay? So towards the normal happens. Slow down is equivalent to towards the normal. Towards the normal. For water wave, how to see it is towards the normal? Okay, let's see. You look at this. You look at this picture here. First, we need to know where is the normal. We need to know that. Okay, so the normal is always perpendicular to the boundary. Like here, this is the boundary that separate the air and the glass. This is the boundary that separate the deep water and the shallow water. So the boundary is here, and then the normal is perpendicular to the boundary. So you can see if the boundary is there. Okay, let me zoom in a bit. So if the boundary is here, then the normal is perpendicular to the boundary. And then this angle from the normal to the wave is known as the I. I is angle of incident. And then after that, reflection happens at the boundary. So it forms a wave disk which is towards the normal. And this is known as R. So that is known as R. Okay, so I is greater than R towards the normal. So next point. So you can see they draw the wave and they draw the wave front also. Okay. Now, when water is sped up, that means getting faster, it is refracted away from normal. Reflected away from normal. Okay, so it happens here. From the glass, when it go out from the glass and go back to the air, so it is getting faster. Then you can see, let's say the angle is here. The angle is here. So what happened is the I is now smaller than the R. The I is smaller than the R. Okay, so which is the I? This is the I. This is the I. This is the R. The I is smaller, the R is bigger. Okay, so, but I have to highlight one thing. For calculation purpose, theory is like this. Whichever come first, that is the I. Whichever angle that's formed afterward, that is the R. That is theory. So theory say that the angle that formed first, I. The angle that formed afterwards, R. Now for this situation, this formed first, this is I. This one formed later, this is R. That is theory. But for calculation purpose, right, we have to know that the big one is I. The small one is R. Okay, for calculation purpose, remember this. For theory, one version. For calculation, another version. So be careful with that. Okay,
In calculation, you said that the big one is I. Actually, what does that mean?
This angle is the bigger angle compared to this, right? So this bigger angle is the I for calculation.
Is it that if if the arrow is away from the normal, then it will produce a bigger angle, and then that is the eye.
The eye. In calculation, yes, it is the eye.
So if the arrow is nearer to the normal, then the angle will be smaller, which will be the R.
Yes, yeah, that's the idea.
Okay, sir.
So of course, I just explain it also. What kind of calculation that I mean, where the big one must be I, the big angle must be I, the smaller angle must be R. So the calculation involve the calculation of the refractive index. Refractive index. Refractive index, we have n equal to sine I over sine R. So n equal to sine I over sine R. So that, I write it down here. So this formula. So sometimes if I don't clarify, then you may misunderstand. I, R, which is I, which is R. So over here, this is I, this is R. Over here, if I follow theory, this is I, this is R. Okay, so should I take the, it's confusing. So because of that, I clarify now. For calculation purpose, the I is the big one, the R is the small one. For this case, same also. This is the big one, I. This one, the small angle, R. Okay, so, and when you count the refractive index, if you get value greater than 1, okay, because big divided by small. Big value divided by small value, you will get answer which is greater than 1. Okay, so that is refractive index, which is involved in the refractions. So that's why we have to take it in that way. Yeah.
Okay,
now understand. Now let's continue. When you explain in words, you say this is I, this is R. When you do explanation in words, but when you do calculation, just remember the idea. Deep water is denser than shallow water. So this one, I don't want to take it, because if I take it, then it will contradict with this one. Okay, so you see, we already set up everything in this way. Deep to shallow, it slowed down. So deep has to be less dense. Okay, shallow must be denser. Okay, so of course I try to make it to be more rational by saying that the water particles are very close together in a shallow region. Okay, in a deep region, the space is large, so the water molecules are further apart. So I try to make it rational by explaining it that way. Okay, so this point, just ignore it. Now let's see here. From deep to shallow. When water wave travels from deep to shallow, speed decreases. So deep to shallow, slow down, speed decreases. Okay, which is true. Wavelength decreases. So here, wavelength decreases. Frequency remain constant. So here. Okay, let's talk about wavelength. Wavelength and speed. Okay, wavelength, you can see it in this way. You see these are the wavefront. The vertical line here are the wavefront. And we say that between one wavefront to another wavefront, that is the wavelength. And now they say wavelength decreases. So you should expect, okay, I zoom in. When you draw, you have a big wavelength to a smaller wavelength. Okay, so this is bigger and this one is smaller. So the wavelength decreases. So make sure you make the line closer together when they enter the shallow region. Okay, so this is the opposite way. When water wave travel from shallow to deep, speed increases, wavelength increases, and frequency remain constant. So this is just the other way around. So we settle this part already. Refraction, settle. Okay. Now let us look at the next one, reflection. So reflections, there's a few words only. Wave bounce away from surface at same angle that strike it. So the wave strike the surface and then bounce away with the same angle. So what is meant by the same angle? The angle is here. Count from the normal. From the wave to the normal, this is I. This angle form first. So this is I. And this angle form afterwards, this is R. Okay, so this R is angle of reflection. Just now the R here, angle of refraction. Okay, so this is reflection. Now, angle of incidence equal to angle of reflection. Same angle. Not like just now, you see, just now the angle becomes smaller or the angle become bigger, but this one, same. Speed, wavelength, and frequency are unchanged by reflection. So you have V equal to F lambda. Same, and same. The only thing that changed is the direction. Directions of the wave change from going down to going up. Direction change. Other than directions, we have speed, wavelength, frequency, all same. Angle also same. Okay, so maybe I should put it in a table. So we have speed, frequency, lambda, angle. Okay, so in refractions, so and reflection. Okay, let's compare. So S stand for same, C stand for change. Okay, so wave speed change, frequency same, and then lambda change, angle change, one more direction of wave change, reflection same, 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 change. Okay, so refraction just means bounce off. So for example, the water wave reach the wall and then the water wave bounce off. Like example again, the light reach the mirror, then the light bounce off. So that is reflection on the light. Okay, let's see diffraction quickly. Diffractions is where the wave bends from straight wavefront to curve wavefront. So it become curve. Okay, so in what situation the wave bends in this way? So when it passes through a gap, or when it passes through an obstacle. So obstacle means something to block the wave. So if you have something to block the wave, then diffraction will happen. So for example, obstacle. So you have a mountain, the wave move in straight. So after passing through this obstacle, so they start to diffract. So diffraction, start to bend, So that is diffractions. Okay, diffraction happens there when there is an obstacle. Okay, then if the wave passes through a gap, so it bends also. You see, from straight, now it bends. So they put 3 diagrams here just to let you know that if the gap is small, how small is it? Like the size of the wavelength, then you can see it bends a lot. If the gap has size greater than the wavelength, you know, wavelength is here to here. If the size is greater than that, then it doesn't see the bending clearly. Okay. Wider gap produce less diffraction. You see, this gap is so wide compared to the wavelength, so you see they don't bend that much. They are like kind of straight. When the gap size is equal to the wavelength, maximum diffraction occurs. So you see, the gap same with the wavelength, then maximum diffractions. So, which means bend a lot. Okay, so we have done everything in the first part.